So we're going to look at function characteristics today, just the basic things, and some of these you've definitely studied before, but we're just going to run through them just so we know exactly what to expect when we're dealing with it in pre-cal. So the first thing we're going to look at when dealing with a function is the domain. And so these are all the possible x values that a function could have. And graphically, it's left to right. Which makes sense because your x-axis, so x values, domain, your x-axis is left to right. And so just a couple of examples, if you are given a function in the table, let's say the x values are 3, 5, 7, y was 4, 6, and 8. So you have a set of points 3, 4. Your domain is the set 3, 5, 7. And so then if we just make up a function and it can look however it wants, we'll say -4 and 5. And I'm just looking at domain, so I'm just going to label the x-axis. If I have a function and it starts, I don't know, somewhere up here and goes some weird whatever places, it is a continuous function, but it does have a definite starting point and a definite stopping point. So those solid black dots mean that it does exist there. The function is true, it works. And so when we describe the domain, we are going from the left side all the way to the right side of the function. And so it includes all of the x values in between. And so we write this in interval notation, and so the lowest that it gets is -4, and the highest that it gets is 5, and we use brackets on both sides. So then another example, we'll say this is -1, and it goes all the way to 2. And so this is also a continuous function. It has a definite starting point, and it does have a definite ending point, but it doesn't actually reach this 2. And so how we write that is with a still interval notation, but we start with -1, so solid dot is that bracket, and then that open circle is a parenthesis. And so that just means it gets really, really close to 2, it approaches it, but it doesn't actually reach it. And so we'll have one more example of domain. And so we'll make it look like a parabola. And we'll say this is at 2. And so if you'll notice, it's a mostly continuous function, but at this point right here where there's an open circle, it doesn't exist. It stops. For whatever reason, it just doesn't exist there. And so the left side has an arrow and the right side has an arrow, which means that the function continues forever. Even though we have stopped it when we drew it, technically that function continues forever in the negative direction and forever in the positive direction across your x-axis. And so how we write that, we go all the way to -infinity. So all the way from the left, we follow the whole function until it stops at this open circle. So we draw it as not continuous. It doesn't exist at 2, so we use parentheses. We use this fancy symbol of union. So we're saying it goes all the way from -infinity. It stops at 2. We'll take the 2 out, we'll break it up, and then the function starts back immediately after 2, and it continues forever in the positive direction. So that's kind of funky. A lot of parabolas just go from -infinity to positive infinity. Lots of functions do that, and that just means all real numbers. It exists everywhere. So with domain is typically partnered with range, and range is your possible y values, so you probably could have guessed that. And this is graphically bottom to top, so you're still going from negative to positive. And so if we look at it at a table, we've got our x, y, 1, 2, 3, 4, 5, 6. We would write the range as a set for 4, 5, 6 because it's only the y values. So now we're looking bottom to top. So if we have a function and say it's here mainly, my function is only existing in a certain section of the graph. So it's a really ugly graph, but that's okay. And so my range now, still in interval notation, we go from bottom to top. So the smallest value is -2, and the largest value is 3. And we've got those closed circles and my continuous function up here. So we write the range as -2, 3 in brackets. Okay, so here we'll continue. Have another graph. We'll have an open circle. We'll make it look kind of like a cubic function. So we'll say this is -3. And so if you'll notice, we're still looking bottom to top. So the very bottom of the function is a -3. It is an open circle, so we would use parentheses. And then the top, we have an arrow. So it is pointing in the positive direction. So we know that it is going to approach positive infinity. So in interval notation, we start with parentheses and a -3, and my function continues forever in the positive infinity direction. And since we never reach infinity, we use parentheses there as well. We'll look at one more. We'll have a discontinuous function. We'll just make it a linear function. And so this range, we're still looking bottom to top. This arrow tells me I'm going forever in the negative direction. I'm going forever down. And then this arrow tells me I'm going forever up in the positive direction. So range is really helpful with your end behavior, and we'll get to that a little bit later. So this function is almost continuous the whole way, except for this spot at 1. So my range, it goes forever down, so we'll go -infinity all the way up until 1. Take the 1 out, and it continues forever in the positive direction. So that's your domain and range. It's super helpful in understanding functions. We'll go over a couple of things. X-intercepts. That's where your function crosses the x-axis. So that is when your y is 0. And so you find that two ways looking at the graph. Or solve equation when you substitute in a 0 for y. So you've been doing that ever since you first started learning about functions, but I just wanted to remind you because sometimes we forget some of the easy stuff. So your y-intercept is where the function crosses the y-axis. And so you find it almost the same way, so you can either look at the graph or you can solve your equation when x is 0. And so a lot of times it's a lot simpler to find the y-intercept because when you plug in an x for 0, a lot of the stuff cancels out. When your x-intercept, when you plug in a y for 0, that's typically where you end up factoring, or it gets a little more complicated. So in addition, so your x-intercepts are typically could also be called your roots or your zeros. And so you find those the same way as x-intercepts. But I do want to remind you that real zeros are on the graph. You can actually physically see them, but you also have imaginary zeros. you can't see. And so this is really where you want to make sure you know how to factor, you know how to use the quadratic formula, you know how to complete the square. So roots and zeros, basically x-intercepts. And so the last thing I want to talk about functions is your end behavior. And so not a super mathematical definition, but end behavior basically means what in the world is going on at the ends of the graphs. So basically, what are your arrows doing? Are they pointed up? Are they pointed down? And so if you were going to describe it really simply, you would have some up, 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 down, up, down kind of thing going on. But when we write it mathematically, we're looking from the left side. So as x approaches negative infinity, which makes sense if you think about a number line, when x is going towards negative infinity, that's going to the left side. So what does your left side do? And your end behavior is telling me what your f of x is doing. So while x is getting smaller and smaller and smaller, what is your f of x doing? What is your y doing? Is it going also towards negative infinity? Is it stopping at an asymptote? Is it going forever in the positive direction? And then, so the other end, you want to check, as x approaches positive infinity, this is as you're going on a number line, it's going to the right. What is your f of x doing? And we'll practice a lot with that. We'll do two really quick examples. So if you've got a parabola, I'll zoom in there. This is my left side, this is my right side. Both of the arrows are pointing up, imagine that. So as x is getting smaller, as it's approaching negative infinity, we are going to the left-hand side. F of x is going up, so it's going towards positive infinity. And my x on the other side, as it is increasing in value, as we approach positive infinity, this will always stay the same. It's your f of x that changes. F of x is still approaching positive infinity. So we'll see if we can sketch one more itty-bitty example. We'll look at a cubic function, and we'll just make them both continuous. So they both start, so we're looking at the left and the right. So my left side is this one. It is pointed down, so my end behavior is approaching negative infinity. And then my right side, so as my arrow on the right-hand side, it's pointed up, so f of x approaches positive infinity. And so that's a real quick explanation of all of the function characteristics, I guess you could say. And so we'll apply those to all sorts of functions.